just have your attention, please. Turn this off. Amazing. Let's start with what I've written up on the board, which hopefully is a little bit of revision. If this is my equilibrium reaction here, then Ka is going to equal just these concentrations. I've left out water. I could put it here, couldn't I? But I don't need to, do I? Because it's only going to have a value of 1, isn't it? Because this is going to be in aqueous solution. Water is amphoteric. Do you remember what amphoteric means?
They can react as a base and an acid.
Yes. So it can act as an acid or a base. So we do need to remember that. And if we've only got water present and it does dissociate out into the two ions, the hydroxide ion and the hydronium ion, we can demonstrate that this is the case. If I, instead of having my 2 there, if I write another H2O over here, I can see that one has accepted proton and the other one has donated proton, hasn't it? So if I drew a line like that, what's the water acting as, an acid or a base here? Is the blue water acting as an acid or a base? And what about our black water? Okay, you can talk to the person near you and see if you can come up with an idea briefly. 10 seconds. Because what is the Lowry-Bronsted definition of an acid? A proton donor. So what's a proton? How else can we represent a proton?
Hydrogen ions?
Hydrogen ion. So which one of my waters here has donated a hydrogen ion?
Black.
The black one. Because it's got one less hydrogen ion over here, hasn't it? So this one's an acid. And our base is a proton acceptor. And so here, have I got that round the right? Oh, yep. So this one's donating the proton. So this one, sorry, that one is the acid. It's donating the proton. Got them around the wrong way.
It accepts the proton.
Oh, you're right. I had it right there. Did accept. No. We have to look at our reactants. Which one? Yeah, the one that gave away its proton is the acid.
Yeah, so the black one gave a proton to the blue one? Because the blue one became positive?
Black one, yeah. Okay, yeah, so the black one has to have given it away to become the hydroxide ion.
Yeah.
Yeah, so that, yeah. Good, I'm glad we sorted that out. Right. So we do know that if only water is present, that we use this constant for K. This is on your formula sheet. And so that means that the concentrations of both of these ions is the same. So we can say then, in a neutral solution, the concentration of the hydronium ion is equal to the concentration of the hydroxide ion. Note that we're not saying that there are none. We're saying that there are always going to be some, but if the solution is neutral, then they're present in equal concentrations. If it's acidic, then the concentration of the hydronium ion will be greater than the concentration of the hydroxide ion. And if it's basic, the concentration of the hydronium ion will be less than the concentration of the hydroxide ion. But because these are all in solution, all in water, this applies as well. Okay, so we still have the dissociation of the water present even in an acid or a base. So let's sort of keep that idea in our minds while I get you to answer the following questions. So can you determine whether the following are acidic, basic or neutral? That's the first question. And you can phone a friend next door, and then I want you to calculate the concentrations of the hydronium ion and the hydroxide ions in solutions with these pHs. So pH 9, 3 and 11. Okay, off you go.